So I'm gonna try to write on my iPad and like also have the computer video and audio going, which I haven't done before. So if something starts going wrong, please let me know. Because I'm not sure that I'll be able to catch it before you all. Okay. Okay, can you all see that? The slides?
Yep.
Okay. Cool. Before we get going, does anyone have any questions about geeks or computers or anything? All right. To be able to see.
What's that weird noise coming from your audio?
I don't know. What does it sound like?
I don't know. It kind of sounds like a demon is trying to like talk to you, but like very awful.
There is someone in my house right now also on an online class that I think she's taking. So it might be that.
Okay. It might just be me because
That's like a hissing.
Elizabeth says she doesn't hear anything.
Okay. Yeah, unfortunately, I don't have a great way around that.
As
I don't
the
have like a microphone or anything. Yeah, I guess we'll just hope that it isn't too bad. Okay. It's not that bad. Okay. Yeah, sorry about that, but we'll just get going. All right. So my name, before we start, is Oliver. I'm a master's student in data science here at University of Michigan. I went to computer science here for my undergrad. And I'm in my second year of my master's program. My research involves identifying, characterizing, and generating like ecological networks. So if you're interested in like network theory or machine learning or anything like this, that's what I do. I've taught 281. This is my 6th semester. So I think I'm actually the most experienced one on staff this semester, which is exciting. Yeah, I enjoy the material and I like teaching it, and definitely I'm happy to answer any questions you might have about the material or anything. But yeah, so you can get going, and if you have any questions, just definitely like butt in and let me know. Okay, so we're going to be talking about arrays, linked lists, stacks, queues, and Deques. Here are just some deadlines that you want to know about. A week from today is the project 1 deadline, which is probably the most important one. And then this is more for you than for me to tell you. Okay, so we're going to talk about complexity analysis, arrays, linked lists, stacks, queues, and Deques. I hesitate to say intro to complexity analysis because I believe that you all took 203 and you should have received an introduction there. Okay, so we're interested in complexity analysis and discussing the idea of asymptotic runtime. So what does that mean? That means how does the length of time that a program takes to run, how does that scale with the size of input that you give the program? So the question is usually if I double the input, how does the runtime of the program react? And typically, especially in examples in this class, we're not talking about seconds, like time as we perceive it. Although when you get to larger data sets and more complex algorithms, you do have to be concerned about that. But a lot of the times we're concerned about the number of steps it'll take. So typically there's like a loop or a recursive call or something, and we're just interested in like how many times will the loop run, how many times or how many levels of recursion will be executed, something like that. So uh, 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 if we want to talk more colloquially about it, when we double the input, if the runtime stays about the same, then we usually say it's around O of 1. If the runtime also doubles, then it's scaling linearly with the input, right? So that's O of n, and then on from there as any function of the size of the input. And again, I'm sure most of you know this from 203. Okay. When we look at asymptotic runtime, especially, well, always, but also in this class, just ignore constants and basically just narrow in on the largest term, right? So you should have an idea of the hierarchy of the growth of functions. So you should know from log n, square root of n, n squared, like polynomial in n, and then factorial and exponential, so like 2 to the n to the n. You should have an idea of like what is the hierarchy there and which one will be asymptotically the largest, which we can talk a little bit about if anyone wants to. But yeah, I guess just let me know. So, if you see something really, some gross polynomial like this, all you really have to be concerned about is, you don't have to say O of 5n squared plus 16n plus 47. Sorry, I'm using my mouse without realizing that I'm actually recording my iPad. All we need to be concerned about here is this part. And in particular, all we need is n squared. So the asymptotic runtime only tells us how the runtime scales with the input size, not the actual runtime of the algorithm. Which I think is just another way of saying like, we're not saying like, I'm not interested in you telling me this is going to run for 10 seconds. I don't care. I just want to know how, if I instantiate the algorithm with a larger data set, how is it going to react? Okay. So just as a little practice, which of these has a better time complexity? So I don't know if someone wants to chat, or if you could say like yes for foo and no for bar or something. Okay, so we're saying which has like a smaller time complexity here. You can talk to whatever y'all want to do. Okay, I see a lot of foos. Looks like the person that said bar would then say foo. Yeah, so usually I think there's a bit of confusion about better. Usually when we say better, what we mean is which one is going to be more efficient on like independent of the input or asymptotically. Yeah, so everyone's saying foo, right? This is the problem here, right? We have this, and then there's that. So what would if I was going to put complexity bounds on these, what would foos be? Yeah, foo would be O of 1, and bar, yep, O of n. Right, and we're just saying this because in foo, no matter the size of the input, we're always running for, I don't know, what is this? A billion? 1, 2, 3, 4, 5, 6. Okay, so 100 million steps, regardless of the input. Whereas in bar, we're running for the size of the input, in this case, n. So it scales with the size of the input, and it scales linearly. If this was, for example, n times n here, then it would be O of n squared. Okay. So which algorithm is usually going to run faster? Does anyone think? Elizabeth says O of n. Yeah, so bar is normally going to run faster because you would think that well, first of all, nobody cares about running these loops in the first place. But if they did, then hopefully their input would be less than 100 million on average. But maybe not. Who knows? I think the answer here is going to be foo. Sorry, bar. Yeah. Okay. So that is what we did on the last slide. And we're moving on. Are there any questions about how we got to where we are with this? Okay, let me keep going. Okay, so we have a few different ways of describing asymptotic runtimes. Big O is an upper bound, big omega is a lower bound, and big theta is a tight bound on the algorithm. We tend to use big theta in this class because big O is a little bit arbitrary sometimes, as omega can be symmetrically. So an algorithm that is theta of n is also both O of n and omega of n. And that is basically why we use big theta for this course. But yeah, all you need to know essentially is big theta is the one we want. Okay. The substitution method and master theorem will be covered in the next lab, but that is how you can solve some of these problems. Okay, so let's look at the complexity of this function, 3n cubed minus 3n squared plus 4n plus 2. What is the term we care about? Right, so we have the biggest term. Yeah, so we have these terms, and I circled around the point of the term. Yep. So 3n cubed will grow faster than 3n squared, and 4n and 2. This is easy with polynomials, right? Because typically the biggest term is just the one on the left. Okay. So 3n cubed, which means if you were to give the simplest big theta of this function, what would that be? Would be, Melody says D. Yeah, that's correct. So O of n cubed is the simplest bound that we can give that that accurately bounds f of n. Okay, so with that in mind, which of the following statements are true? A, f of n is O of 3n squared. I don't know, can you vote or chat or yes or no? Hello? Oh, I'm sorry. My audio cut out. Yeah, my internet is not great, unfortunately. So which of the following statements are true? Is A true? Is the question. Okay, so let's see here. So you're saying f of n can be bounded by, okay. Right. So our largest term of f of n is n cubed, and that's going to grow faster than this, which is n squared. So f of n cannot be bounded by 3n squared. So that one's not true. How about b? 3n cubed minus 3n squared. Yes. Yep. So b is true. How about c? Getting some yeses. Melody says no, wait. Melody, are you convinced that 2n cubed can bound f of n? Remember, we're just looking at the largest terms. So we're interested in anything that can bound O of n cubed. And this is also O of n cubed, right? Because we can forget the coefficients. Exactly. Yeah, Melody. So always you can remove coefficients. We're just concerned about the largest term, basically. I mean, if you want, if you're interested in like more delicate complexity analysis of things, researchers end up caring a bit more about coefficients and what they're likely to be and such. But in this class, just don't worry about the coefficients at all. Okay, D, we already said is good. And how about E? Can O of n to the n bound f of n? Elizabeth says yes. Yep. So n to the n bounds any polynomial. And it also bounds exponentials of the form like 2 to the n, is obviously O of n to the n. So n to the n is one of the, probably like the largest function. Hamad makes a great point. Yes, it's not a tight bound. So exactly, like D could be considered theta, as could C, as could B. This is actually, I'm sorry, this is not true. But this cannot be theta, because it's like arbitrarily larger. Like, yeah, of course, n to the n is larger than n cubed. It doesn't tell us anything about our algorithm, whereas B, C, and D do tell us something about the algorithm. Okay. Any questions here? So all of these are right. Okay. We will move on. Okay. So consider, these are the answers. You did a good job. Okay. For which of the following pairs of f of n and g of n is f of n O of g of n? All right. So for A, 1 plus n over 6 is So what is big theta of f of n here for a? F of n equals 1 plus n over 6. Yep. So that is, I'll just do this. The tightest bound we could get here is theta of n. Now, how about g of n? G of n root n plus 5 log n plus 7. What's the tightest bound? Okay, Hamad says square root of n, and that is, okay. Elizabeth says log of n. Yeah, so square root of n is actually larger than log of n, which I think if we go to, yeah, I don't know. I would say like basically go to, I believe, desmos.com. And you can plot out the graphs, and it's actually a very useful tool for complexity analysis because you can see all of the functions next to each other. Let me just make sure that I didn't give you like some horrible website. Yeah, so just go to desmos.com. There's a graphing calculator there if you're interested. But the point is square root of n grows faster than log of n. So this is theta of root n. Okay, so from this, what can we say about A? Is f of n O of g of n? I'm looking at the at like the at y'all's list, so you can type yes or no if, or you can like use the yes or no buttons if you prefer that. Okay, and I've got chat up, so I'm totally covered. Whatever you want to use. All right, so everyone's saying no, and that is correct. So f of n cannot be bounded by g of n because g of n is theta of root n, and f of n is theta of n. So of course, f of n is going to grow more quickly than g. Okay, now let's move on to b. Okay, so b is 3 to the 3 to the n, 3 to 3 to the n, and g is 3 to 3n. What do you all think? No? Okay, so f of n, I would say here is, I'd probably just say like theta of 3 to the 3 to the n. There's no real way around that. And g of n, I would say is like theta of 3 to the n, because I'll just drop the constant off the 3. So yeah, I think no is the answer here. No, no. Because obviously this term is less than that term. Okay. All right, how about C? 4n squared and 2n squared minus 10n. What is the theta of 4n squared? Yep. And what's the theta of g of n? Elizabeth says same. Yep, also n squared. Okay, so is f of n O of g of n in this case? Yeah, of course. F of n is bounded by n squared. G of n is bounded by n squared. Easy. Okay. So we'll take this one. D, f of n is log of n, and g of n is log of n of n over 10. What can we decompose g of n into? Who knows their log rules? Yeah. So log of x over y equals log of x minus log of y. So here we can say log n minus log 10. And then I think it should be clear here what the answer is. Natural log or log doesn't matter. We can just use the change of base formula, and it's just these. It's like they're equivalent, right? Because natural log is just base e. In terms of complexity analysis, I mean, not generally. Okay, so is D? Can you give me a yes or no? Is f of n O of g of n for D? Okay, yeah, it is, right? The largest term from both is this right? It's the same thing. And then G just has this constant behind it, which we don't care about. Yes. Okay, good. All right. Let's go back. What? Okay. F of n is log of n squared times 3 to the n, and g of n is 6n plus 9. Okay, so this is pretty confusing. What can we break that into? If I wanted to manipulate log of n squared 3 to the n a bit, what could I do with that? Okay, so Sam has an answer for us. The first step is log of n squared plus log of 3 to the n. And then we can use the log rules to do 2 log n plus n log 3. Okay, so now we've got, this is f of n. Okay, and then if we, let's just strip out the constants, and what do we have? I will say that this is proportional to n plus log n. Okay, so where are we at here? Can g of n bound f of n? Yep, it is correct. Yep, because the largest term here is linear, the largest term here is linear, so we're good. Okay. Yeah, we did it. I thought for a second I had chosen B, but good. All right. Any questions about this problem? Okay. We will move on. All right. We're going to look at the time complexity of this code. And this is like straight out of a exam problem. So this is very similar to what you'll see on the midterm. We'll give you a chunk of code and we'll say, what is the complexity of this code? And we'll try to do like something cute and tricky and be like, there's recursion. So I would definitely recommend like trying to maybe like write a couple lines of code for a friend or something and seeing if they can figure it out, because that is all we do. Okay, so when I look at this, what I see is I see a for loop and I see an if statement that seems to be calling a function. And those are the things that I'm concerned about. This is constant time. That's nothing. Nothing else happens down here. Okay, so we're just concerned about these two lines, basically, the for loop and the if statement. Okay, so the hint tells us that binary search is an O of log M process where M is the number of columns in our 2D array. So what does that mean for the if statement? What is the if statement run in? Fast to the trigger there, Elizabeth. Yeah. So the hint is telling us what the if statement is. Can anyone just type it in the chat? Yeah. So we've got this line is going to be log M, right? Because we have an n by m array. So m is the number of columns. And then what's the for loop going to be? Okay, Elizabeth. Yep. So Elizabeth has it. The for loop is just looping over the rows, right? So that's n, and it's not doing anything besides, it's incrementing by 1 every time, and it's going to the full size. So that is, we'll use theta here. Theta n. Okay. All right. So Elizabeth says n log m for the entire thing. Does anyone have any other ideas? Yeah, I think Elizabeth is right. So the way I would read this is for each of n steps, I'm doing a log m process. So I would, usually when things are nested, that's when you would use multiplication in the complexity. So n times log m here is correct. One thing, something that obviously you'll have to watch out for in the exam is like if we tell you that it's an n by m array, then making sure that you don't put, like theta of n log n here, like makes sense to you, but it's not the answer. I'm just learning about all these fun colors on the iPad, so I'm trying to use them. But yeah, so that's what we're doing. So n log m is correct, and n log n would be incorrect, even though it seems, like intuitively you're like, well, yeah, just call it n, it doesn't matter. Okay. Here's a bit of explanation that if you want to go through later, you can do, but we just did all that in words, so I'm gonna breeze past it. Okay. if you have an algorithm with 2 steps, when do you multiply and when do you add? So we were just talking about, when you might multiply, but adding would be if you do something and then you do something else, and they're independent of each other. Besides that, it's like a synchronous process. So like, yeah, in this example, you iterate over x, and then you're done with vector x, and then you iterate over vector y, and then you're done with vector y. So we would add those complexities. If you are doing something with the elements of vector y for each element of vector x, then you would multiply, because it's that for each that gives us the multiplication. So this is O of x times 1. Theta of x times 1. Okay. Sometimes it's harder than just looking at a polynomial. And in that case, we have a bunch of tools that we can use. In this class, we'll go over substitution method and master theorem. If and when you take EECS 376, you will be going over more tools. And then if you go on to get a PhD in complexity analysis, you'll probably learn the whole thing, which is not what I'm doing, so I don't know about it. But for this class, all you'll need to know is substitution method and master theorem, which will be next lab. Okay. Arrays or linked lists. Does anyone have any questions about complexity analysis at all? Generally, I mean, like the concept of the entire thing is pretty strange, so any sort of questions reasonable. If I could get some feedback from most of you, that'd be great. Okay, Sam, what is the difference between amortized and average? That is a great question. It will be the topic of, that will be one of the topics of next week's lab. But essentially amortized and average very often are closely related to each other, but it's not always the same. So in averaging, we're usually looking at like what is the cost of an operation in terms of the total like population number of operations. Whereas amortized, we can break it down a little. We can choose our granulation basically. So we can say that we want to spread the cost of one operation over, it could be a function, it could be n over 100 operations. It could be, I want to just spread this operation over these 10 operations. In terms of, you can look at it outside of computer science. You could say, I want to amortize the cost of my gym membership over the days of the month, which in that case, it is equal to the average. Well, if you say that all the months have the same number of days. But yeah, there's a little like nuance there that is not often needed in 281, but it is important, and we'll talk about it next week. It's a great question. Swathi, in the second multiple choice question we did, can you explain why B isn't true again? I think it was slide 8 or 9. Yep. Okay. Go back up. You looking at this one, Swathi?
Yes.
Okay. Yep. So I'll just do it down here because that up there is a mess. Okay. So for f of n, we can no longer break down 3 to 1 because the coefficient here does matter. Because obviously, like 1, sorry. Right, because 1 to the 1 to the n, sorry, my pencil is being slow, is equal to 1. So the coefficients here matter. Hello. Okay. All right, 1 to the 1 to the n equals 1. So the coefficients here do matter. So f of n is the tightest bound that we can get on it is I'm sorry, I didn't. Okay, here we go. Is theta of 3 to the 3 to the n. Okay, we can't get any. We can't get any more granular than that. That's the simplest form of that complexity. And then g to the n, whenever my iPad catches up. Swathi, could you answer, is there anything we can simplify about g of n?
Maybe just a constant in front, like the big 3.
The in the exponent
Or sorry, the exponent. Yeah, the
Yeah.
exponent.
Exactly, yeah. So we can simplify the exponent to be 3 to the n. Okay, so these are our bounds. And if it's an issue, like whenever you have like something exponentiated and then that has an exponent as well, it's just like that's going to blow up basically the growth of that. The growth of that is very high. How do I want to explain this? Yeah, basically like f of n here is just going to grow extremely fast, and g of n is growing quickly, but just not as fast. If you're confused about like the growth rate of these functions, then I would suggest putting it into like Desmos or a graphing calculator or something. But anything where it, double exponentiation is just very, very quickly growing. And I think like for the purposes of this class, as long as you're comfortable with, is this function going to grow faster than another function generally, then it's fine. I think the way that I would think about this is like, let's just compare the exponents because the constants in front are the same. So like this one would be 3 to the n, and this one would just be n. And it's clear which one of those will grow faster, right? So if the exponent of f of n is growing faster than the exponent of g of n, and they're both exponents of the same coefficient, then I think f of n should be growing faster. Does that make sense?
Yeah, thank you so much.
Okay, great. No problem. Okay, a lot of good questions. Thank you. All right, arrays and linked lists. 2 things you already know about. We'll just talk a little bit more about them, and we'll do a couple like algorithm questions. Okay, so these are like 2 basic ways to represent lists in memory. As we all know, the first thing that should come to mind when you think of arrays is contiguous memory. On the computer, all of the data is stacked together in one place. Whereas a list can be all over the place, right? You should have learned this in 280, I think, where lists can be distributed throughout the memory, throughout the stack or the heap or wherever they end up being. So yeah, I think, like as long as you understand that, then the rest of this class's understanding of those two things will follow from that. The key thing here to remember in practice is that pointer arithmetic is only going to work for arrays because adding to a pointer when it's a linked list just puts you like, you're not really sure where it's going. But in an array, it makes sense because it's the memory is all stacked on top of itself. So here's a bit of just like runtime analysis on different operations for arrays and linked lists. I'm not going to go over this like line for line, but this is a good reference slide and something that if you're not completely comfortable with arrays and lists, might be good to put on your like sheet for the midterm. Yeah. Although I guess with take it home tests, it's like you have more than one sheet. Okay, so here's a bit about pointers, which you will barely ever have to use in this class, but we'll talk about them anyways. Pointers store address locations, so you'll have a pointer on the stack or whatever in your local memory, and then or in your local scope, and then it'll be pointing at some variable which contains the data. So that's a declaration. We're getting the address with the ampersand in front of num. Multiple pointers can point to a single address location, no problem. You can do that through the assignment operator. And then arrays are pointers, like the variable that you have that is representing your array is a pointer. So like all of the pointer arithmetic works with that. Can anyone tell me what the result of that line will be? You just type it in the chat. What is a pointer to second element? What is, we don't know what's in index 2. You're right, we don't know what's in index 2. All right, so what's the first thing it's going to print? Like what's that part going to print? What's number 1 going to print? And then we'll talk about what number 2 will print. Yeah, so the first one is going to print 5 because array at 1 obviously gives us this. And then array plus 1 will be pointing here, right? Like this pointer will be pointing to number 1 or index 1. And then we just dereference that. So it's going to print 5 as well. Okay, any questions about that? So new is pointer to first element. Are you talking about the first line here, Sam? Yeah, okay, so that as this shows, it should be pointing It points to here, right? To the 0th index. Yeah. And then so when you do +1, you get the first index, which would be the second element. Yeah. Yep. I know this is like the first half of 280, and it's like no one wants to deal with pointers ever. And we won't make you deal with pointers very much, but we just want to make sure that you're up to date with them. Okay. Any other questions about this? Okay, I'll move on, but I'm looking at the chat. So. Okay, strings, vectors, and other auto resizing containers are implemented with arrays, which reallocate and move the data when needed. This means that if you have a pointer, so you have like some array, and it's got some data in it. Maybe. Okay. It's got some data. And then you have a pointer pointing to one of those pieces of data. Then let's say you want to put a new piece of data in there. That's going to reallocate, right? So you've got like a vector v. V. It's going here. And then you're going to reallocate. And it's going to move down here. And it's going to, so I don't know why it's being so slow. Good learning experience. Yeah. I'm sorry, y'all. But basically, like you're gonna have the pointer will still be pointing at the array with the old data before it resized, and then your new array will not have any of the correct pointers pointing at it. So you need to, let's see if it will let me draw. Okay. So you need to be really careful about that, basically. 2, 3, 4, 5. Okay. Yeah. And then you have your new element. And then, yeah, so then this part would go away. And now your pointer, like this pointer, is still pointing at, this, but it's just junk memory now. So you need to be careful about having it point to the new one. Okay, linked lists don't have this problem because the memory doesn't move. So here's an example of this happening. Again, so I guess I didn't need to draw it. But if you're curious about this again later and want to think through it, that's a good place to do it. I guess, are there any questions about this? Does this make sense? This is important for project 2, so you don't necessarily need to know it right now, but just in the future, when you think about having pointers to data structures, think about if that makes sense and what you need to do. Okay. I'm going to move on. All right. Which of an array or linked list is better at when you're given a pointer to an element, inserting an element directly after that. The pointer should be a giveaway.
I have a question about the lab.
Yeah.
So on the files, it says like bonus written problems. Are those required, or are those just like for practice?
No, it should say ungraded next to it.
Okay, thank you.
And that is true. Yep, so I'm seeing linked list in the chat. That is true, linked list here. And that is true because if you're given an element, a pointer to an element, then all you just need to do a couple pointer moves to insert the element into the linked list, right? But otherwise, with an array, you have to maybe grow the array, and even if you don't have to grow the array, you have to move a lot of data in the array. So yeah, linked list is definitely better if you're given a pointer to the element to insert a new element after that. Generally, like in random insertions to a data structure will always be better on a list. Okay, given an index, update an arbitrary element. What's better for this, array or linked list? Array. Yeah, for sure. I mean, this is like what an array is built for, right? Random access. Okay, search on a sorted container. Yep, seen some more arrays. Yeah, that's true because of random access on an array is O of 1 and random access on the linked list is O of n, right? So if you're searching on a sorted container, that means you probably want to use binary search, and binary search requires random access. So arrays are better. Okay. Removing multiple elements from a container. I mean, the question could be like, remove a single element, right? Either way, it's going to be the same. Yeah. Linked list, right? Because you just have to do pointer movements instead of moving all of your data. So it's an O of 1 operation instead of O of n. Yep. Okay. Any questions about those at all? All right, we'll keep it. Okay, this is just text explanations. What we just did. Okay, here's the problem. Given an integer k, find the kth to last element in a singly linked list. You do not know the length of the linked list. Who's got an idea for how you could do this? So let's just think about like, I guess I could like make you all go into breakout rooms. For now, I think I'll give you an idea, like the first idea you could have about this, and then you can maybe add on to that. So, you know, the first idea I might have is go go find the size of the list with a single pointer. Just start at the beginning, go to the end. Does singly linked have an end iterator? Nope. Right, because I mean, it has an end iterator in the sense that like you can tell when you're at the end of the list, but you can't go backwards from it, right? So you could find the size of the list first, and then you could say size minus, second pointer goes size minus k iterations, and then that'll be it, right? For loop that iterates through the list using pointers to get to the end of the list, and then for loop that goes back k iterations. Yeah, so that's pretty much what I just said, right? Except you can't go backwards in a linked list, so you just have to start at the beginning, and you have to go size minus k iterations. Right? So what's like a way that we could do this all in one for loop? No, yeah, sorry, it's just single linked. Can we do this all in one for loop? What do y'all think? Yeah, right. I mean, yeah. So yeah, that's the first way. And then so I guess where I'm trying to get is like if you have k, you can just iterate one pointer k times and then start the second pointer and iterate them together. And then once the second one is at the end of the list, or once the first one is at the end of the list, the second one will be at size minus k, right? Big brain. Yes. The true five head. Yeah. So that's one way you could go about doing it. Does everyone understand that? Okay. All right. Okay. This is fine. You can go back over like the analysis of it later, but okay. So sort of along the same lines, given a singly linked list, let's find an algorithm that returns the value of the middle node. If there are two middle nodes, return the value of the second middle node. So it's there will also be two pointers involved here. What can we do with our two pointers that will give us the correct solution? If they're same, return. If one off, return and one. Yeah, no worries. If the two pointers are the same, we're trying to return the middle of the list, and we don't know where the end of the list is, right? So like analogously to the first one, a solution we could come up with is iterate over the entire list, find the end. Now we know the size, and now we can just iterate like size over 2 times or size over 2 plus 1. But what's like a different way we could do this in one for loop with 2 pointers? Second middle node, I think means the one closer to the end, but let's just forget about that for the moment. Just think about like don't worry about like the first or the second middle node or whatever. Just look at middle node or end node. Point to node and double the node. Check for null. Okay, so that sounds like array arithmetic, but we can't do that because it's a linked list. So you have a pointer, yeah. Second one moves forward 2. And 2 pointers, one that moves through the linked list twice as fast as the other. Yep, exactly. So we'll have a fast and slow. You increment the fast one by 2. You increment the slow one by 1. And then when fast hits the end, the slow one is at the middle. Yep. So there's a lot of these like 2-pointer things for linked lists. But yeah, these are good like questions to think about for the exam. Okay, there's some examples. I'm just gonna get past these. Okay, any questions on arrays and lists? Okay, talk about stacks and queues. Here is the ADT interface for a stack and a queue. We have push, pop, and either top or front, size, and empty. There's no random access. We can't iterate over them. We can't get what's in the middle. All we're interested in is putting things in and taking things out in a certain order, right? So for queues, we want last in, first out. And for stacks, we want first in, first out. Usually for stacks, what I think about is, when I'm like drawing them for like, if I'm trying to solve like a stack problem or whatever for the exam, or if I'm just trying to explain a point, I'll draw a stack like this, and I'll think of a stack with putting things in, taking things out. They're both coming out of just like, it's the only thing. There's one entrance and one exit. You can think of like a stack of plates or papers, right? You're putting down the plates. You can only take the top plate off before you can get the second top plate. When I think of queues, I try to draw something that looks more like an array. And I'll think about it like this kind of. So I think these are useful ways to think about them for during like the exam questions and stuff. But yeah, so that is a stack and a queue. A queue I think about like like a line of people or something. And people are getting in line, and maybe you're like waiting to get a table at a restaurant or something, where order matters, and it's important for you to stay in your position in line, and you'll get helped in the order that you got in the line. So I think that's a pretty reasonable way to think about a queue. All right, here's a stack. We just talked about it. Real life examples, stack of plates. Here's a queue. A real life example might be a line of people. Anything where there's like a line of things and they're all like moving forward, basically. Yeah. One example of a stack in programming is like the back button on your browser is a stack, right? Because you want to go to the most recent page you were at. You don't want to go to the first page you were at. And queues in programming are pretty ubiquitous, but you can think of it like in your operating system. One way to serve tasks that are coming into the operating system is to just have a queue and say like the first task that I need to do as the computer is the first one in line. So Okay, so the rest of this is like a couple of examples of questions that involve stacks and queues. So we'll talk about them a bit. And then you can also go back. I mean, there's like big like animated slides on this, so you can go over this yourself as well. Okay, can you start a stack using only an auxiliary stack and O of 1 additional space? So what this means is someone is giving you a stack, and then you can have one more stack, which is O of n space, but you're constrained that it has to be a stack using that O of n space, and you get only constant extra like space beyond that. So like a variable or two, basically. The stack supports top, push, pop, and size. And how can we approach this problem? So I guess let's talk about it a bit. Does anyone have any ideas? So we have two stacks, right? You got no clue. That's fair. It's a strange question. We have two stacks, right? So, you know, we have this full one, and then we have another one, and we've got, I guess I'll write some numbers out. Then we've got 2 and 3 and 1. And we're interested in getting that in order. And we only get this other stack, and we can use like a variable or two extra. Hello. Are you working? 2 and 3 and 1. Oh. Am I losing you all, or is my connection dropping? You can hear me. Okay. All right. Let me keep going. Okay. So 2 and 3 and 1, and we want to get this into another stack, and I would think we at least want one variable, because if we don't have anything in between, then all we can do is flip between the stacks and everything remains in the same order, right? So we need some ability to get something out of the stack and keep it out of the stack for a second while we put some other things in. So, you know, maybe we could pop the 1 out, and if, you know, the 1 will initially go into the variable, and we'll get rid of that, and then we'll pop the 3 out, and the 3 we could say is larger than the 1, so we'll put the 3 into the next stack. And then take it out of the first one. And then same process with the 2 is larger than the 1, so we'll put it into the next stack. And then finally the 1, because there's nothing left in that stack. And look, we've sorted it. Okay, so that obviously a very simple example, but I think that gets us like towards the answer here, which is we want this extra stack and we want another variable, and we're going to be doing like some swapping between the stacks. Okay. Here's some stuff about the problem. So we're pushing elements from the input stack into the auxiliary stack such that the large items are sent to the back of the auxiliary stack, like what we just did. So here's a bit of code that could do that, and you're free to go look at that later if you want. And here's an animation of this happening. So we want the items to be in order 1, 2, 3, 4, 5. And we're just going to accomplish that by moving the items between the auxiliary stack and our single variable that we have. Yep. So, and you'll notice with a bigger example, you have to do a bit more switching than you would otherwise. So, yeah, we did. So I guess we know that in this case, 5 was larger than the top of the auxiliary stack, right? So we had to put the top of the auxiliary stack back into the input stack, and now we can put the 5 into the auxiliary stack, which we know will be good because now 2 will be smaller than 5 and it will be on top of it. So 5 will go down. And now we'll get 2, and 2 is smaller than 5, so that'll go into the auxiliary stack. Now we're going to have to do the same thing with 3, because 3 is larger than 2, so 2 goes back into the input, 3 goes into the auxiliary. Now 2 will go into the auxiliary. Yeah. So this continues for a lot of slides, and I think the important point is understood here is that you can do this and there's a reasonable algorithm to get there. I would encourage you to write code for this because this is very familiar to like the exam written questions. So I would definitely suggest thinking about this problem and then actually trying to write the code for it. So I will leave the rest of like walking through that to you because I want to get to the other questions. Okay. Does anyone have any questions about how that works or how to write the code? It's good exam prep. So definitely go back to it. Okay. All right. Let's see. So we're going to implement a queue with stacks. Here's one idea. One of the stacks is the front and the other is the back. How will this work? Will this work? Let's ask that question. Will, if we're trying to have a queue, but all we really have under the hood is 2 stacks. We're saying that one stack will be the front of the queue and one stack will be the back of the queue. So it'll be like this. And we'll be putting into one. We'll be taking out of here. Does this make sense to you? Yeah, I mean, no, right? There's no like function for getting the elements between places. They're all in the wrong order. It's not totally clear how that is going to work. Right. So if the front stack is empty, then those will just break, right? Front and remove. So there's a lot of problems here. We can but we can do a little rearranging when the front stack becomes empty, and then hopefully it'll work. So what we can do is when we want to pop an element out of the queue, when we want to get the element, we can check if the front stack is empty, and then while there are any elements in the back stack, we're going to push them into the front stack, right? Which will put them in the right order because we're flipping them over, and then we can. We're popping off the back stack as we go, so we're removing the elements, and then finally we can. This is actually like returning that last element, right? Okay. So why not move just one element? Does anyone have an idea why we can't just, when someone requests an element, just flip one over and return it? Let's look at an example maybe. So the order that they're putting things into the queue will be, I can just say 3, 2, 1. And then the order that we'll get things out of the queue should also be 3, 2, 1, right? So okay. So let's say we put those items in that order into the first stack. And this is the stack we're putting in, and this is the stack we're taking out of. Right. And then, okay, so what happens when we just move a single element over instead of the entire stack? The top element is 1, right? So I would just flip 1 over into the second stack, and then I would return 1. So does that do what we want? It'll be the wrong order. Yeah, exactly. So for that reason, we have to move the entire stack, the back stack, to the front stack instead of just single elements. Yeah. Okay. Yep. So there's the answer. And then, okay, so we're going to do this is just a walkthrough of how the implementation will work. But again, I would encourage you to go through and code this in C++ or Python or whatever. And I think it's just good prep for the exam. So first we're going to insert red. That goes in. Really wish there was a smoother way to do this. Then we'll insert orange. And that's in the back stack. Now we're going to insert yellow. And that'll be in the back stack. And now we're going to remove something from the stack. So this is where we have to flip the entire stack over. So we flip yellow, orange, and red. This is done here. And then finally, we can remove the top of that. Looks good. Okay, now we're all done with that operation. We can insert green. Green is going in, blue is going in. Now we're popping. Front has elements, right? So we're still good to just pop straight out of there. And we pop yellow off. And then finally, we have to flip over the stack again so that we can pop green off. Okay. So I really think that with both of these stack questions, it's when it's time for you to be working on the on exam prep, these are great things to come back to and try to program, maybe even try to program them by hand, and then try to program them with the computer and see if your implementation works. But I think these should at least give you like the intuition for the algorithm off of which you should be able to build a program. Are there any questions about stacks or queues or either of these problems? Okay. I think this is pretty much the end. We'll talk briefly about Deques because I think there's quite a bit of confusion every semester about how they're implemented, and then we'll be done. So a deck is just a way that we can have both front and back access, but we want it to act kind of like a vector, and that we want O of 1 access to the front and the back, and we also want, very importantly, constant time random access. So we want to be able to, we want to be able to iterate over them or whatnot. So here's one implementation is just a doubly linked list. We can add and remove from both sides with constant access, but the problem here is that operator brackets is not constant time. We still have to iterate over the list to do that. So another way to do this is we could use a circular array, but this is like complicated and no one wants to deal with it. Let's see. It also, if the array grows, the pointers become invalidated, like we were talking about before. So this is also not a viable solution. So here's like the actual implementation, and I will leave the majority of this reading up to you. But essentially, we have these. They're like chunks, which are arrays, and then there are pointers to those arrays, and there's an idea of the hierarchy of the arrays. So which one is like the front and the back at any current time. So essentially you have a linked list, but the linked list is built of arrays. And so you can store more than one element in each array. And there's some idea about like what are efficient numbers or like sizes for the arrays inside of the linked list and things like this. So you can arrive at this supporting constant time operator brackets. But yeah, so I mean, I think it's pretty cool. It's a bit confusing, but it's a cool data structure. Does anyone have any questions about Deques? It's not something like, we're never going to ask you about the implementation details of a DAC or ask you to like program anything with it. But we're just telling you this because we ask you to use Deques in project 1 and like maybe, in a programming question on the midterm or something. And it's nice. You'll never have to rely on your knowledge of how a DEC is implemented, but I think it's just nice to know what's going on behind the scenes. Because it's kind of like, I don't know, if you think about it a little bit, it's like kind of a magical data structure. Or maybe that's just like the super CS nerd in me. Miracles do come true. Okay. All right. That is all. The last thing is the handwritten problem. Here, notice that you don't have to like, write out all this stuff. All we need you to do is write out the functions, and I think 2 out of the 4 functions are like a single line, so it shouldn't be too bad. All right. Does anyone have any questions at all about the class, about anything we just talked about? Anything at
This
all?
this handwritten thing is that in the bonus things PDFs,
It is
or
not
is
a
this just
bonus.
something at
That's
the
the
end?
one for the lab. What was
Wait,
the last
what?
part of the question? I'm sorry.
Oh, I was just wondering, is this only in the slides, or like where else do we find it?
I do believe it's only in the slides, and you can find it here, or you can find it on Gradescope. I think.
Okay, so this
I
is
don't
what
know
we
if
submit to Gradescope.
this is what you submit to Gradescope.
Okay.
Yeah, I don't know if the problem statement is on Gradescope or if it's just a submission button, but it is definitely here, and I think this is where I would look for it, I guess. Yeah.
Okay.
Melody, yep, need to submit to Gradescope. Okay. Here, since y'all are still here, I'll do the first one for you. You can return, let's see if it's a singly linked list, and we want the front, and we're getting a Q, then I guess it doesn't, we want to do, like I think the front would be the back of the list. So I think you just want to return tail value. But yeah. All right. Well, oh yeah, it's not loading. It should be tail arrow value. I don't know why it's not doing. Okay, there you go. Oh, and I put dot, but it should be arrow. Okay. Do y'all have any other questions? Anything for me? Otherwise, I'm gonna end this. All right. Well, I'm glad y'all stuck around. Have a good day.